the topic today is going to seem a little bit related to last time. So what we did last time is we talked about how to achieve the maximum value out of a polynomial. Well, if you don't want to necessarily maximize, you just want to know all of the possible parameters for which the output is at least this big. For instance, here's one. So going back to sales of Thneeds. So the revenue which the Onslaught gains from sales of Thneeds is given by the formula revenue is equal to negative 1 over 2 p squared plus 1900p, where p is the sales price of a Thneed. So one thing we did last time, this was like the exit quiz, which was it actually an exit quiz? It wasn't, was it? No, it was. Had you determine the price point which maximized revenue? Do you remember just how many people just remember what that price point was? What was it? 1900, which we could compute again. So that's not what this is actually asking about. So revenue maximized at p equal to 1900. And I see that later on I'm deciding, even though I know units aren't specified, I'm calling them dollars. What was the maximum revenue? That wasn't asked last time, but enough people computed it anyway. What was it? Yeah.
It was like 18, I think. 1805, and then like 4 zeros after that, or 3 after that.
I think that was right. Something like 1.8 million?
Something like that.
We could recompute it, but I don't think it's worth the time right now. I'm pretty sure that's right. So here is a question then. Let's suppose the Onslaught doesn't just want to maximize revenue, but the Onslaught wants to have some freedom to absorb other economic changes in his fiscal model. And so just wants to know what price points, multiple price points, will result in revenue exceeding 1 million. Is there at least one price point that has revenue exceeding 1 million by that? Yes. Yeah, we can get it all the way up to 1.8 million, approximately. So let's try to find all of the possible price points, see how much wiggle room there is. So let's parse that out. So what inequality do we need to solve? Yeah.
I just have one of those note things.
Oh, yeah. Good. Anyone else? Excellent. Okay. That explains why I was so particularly low. I failed to count sufficiently many times. Okay, cool. Because I do always put like 3 or 4 extras, because I know I won't be able to count all the time, but that doesn't matter. What inequality do we need to solve?
1 million is less than negative 1/2 p squared plus 1900p.
Yeah, we got 1 million, which it's easier to write 10 to the 6th for a million, so I'll do that. We want to know when is that less than revenue. We have a formula for it. And we have a general plan of attack when we need to solve an inequality. We start by solving the corresponding equality. So let's solve 10 to the 6th is equal to negative 1/2 p squared plus 1900 p, and I'll rewrite that as 0 equal to negative 1/2 p squared plus 1900 p plus, nope, minus 10 to the 6th. Is that an equality which is, well, easy isn't the right word. Is that an equality which you just know how to solve mechanically? Yeah. The numbers are hairy enough, I'd probably just resort to the quadratic formula with the computer aid. So let's do that. So according to the quadratic formula, let's not go there yet. This is solved by p equal to negative b plus or minus the square root of b squared minus 4 times a times C all over 2A. Fair enough. And I certainly am not going to try to do it by hand, but I mean, one should simplify at least a little bit before using a machine to minimize the number of keystrokes you have to make. For instance, I see a negative times a negative times a negative, so two of those negative signs can cancel. And what's 4 times a half? 2. So may as well do that simplification before I do any computation. And what's the denominator of this in this fraction? -1. So division by -1, that's the same as just multiplying by a negative sign. So with that out of the way, let's compute that. So it'll be negative. Well, let's use this one. Negative 1900. Plus or minus, let's do the plus one first. The square root of 1900 squared minus 2 times 10 raised to the 6. And apparently that's like 621. I guess I'm putting dollar signs next to my things as units. So one of the values is around 631, or $31.69. So all I've done is I've written down those two numbers. That's all you used. Nice. So those are the two solutions to equality. Do those agree with what other people did who did it manually? Okay, I didn't do anything wildly incorrect. So now that we found the two solutions to equality, how can we determine the solutions to inequality? We can play this game where we like check values between, check values beyond. And there'll also be a graphing technique, but I want to capture both in this. So let's check some sample points. What is a sample point that is less than 631? 0. Good choice. That's easy to plug in. What is the revenue you get when you plug in p equals 0? 0. Great. Is 0 strictly greater than 1 million? No. So 0 isn't in the solution set, so nothing before 631 is. So p equals 0 produces an r equal to 0, which is less than 1 million. So nothing to the left of 631 is in the solution set. What is a p-value between those two p-values?
632.
632 would do it. Good. Tell me what you get for 632. Or I guess I can actually, of course you wouldn't want to do this by hand anyway. So, negative 1/2 times bigger than 1 million or less than 1 million? Bigger. So everything in between should do the job. So could we have actually skipped that computation? Is there a p-value that we've already plugged in between those two?
1900.
Yeah, 1900. We found that that corresponded to like 1.8 million. So we could have skipped this computation. It doesn't hurt nothing to do that though. So let's see, p equal to 631 produces an r value which is greater than 10 to the 6th. So numbers between walk. What is a number that is greater than 3,169?
3,200.
3,200. Maybe I'll even go more extreme. Let's go like a billion. So like a billion is like a 12-digit number. 10 to the 12th is a billion. And even if it's not, let's just imagine 10 to the 12th. If we plug in 10 to the 12th, then p squared will be like a 24-digit number. Divided by 2, you'll get a 23-digit number at least. And it'll be negative. So negative 23-digit number plus 1900 times p, that's a 12-digit number, times a 4-digit number, so that's a 16-digit number. So a negative 23-digit number plus a 16-digit number, positive or negative? It'll be negative. Like a negative 23-digit number, and then you subtract something that doesn't have as many digits. It'll be negative. But I guess what matters is how will it compare to a million?
Small.
It'll be less than. So p equal to something real big goes to a revenue that is less than 10 to the 6th. So numbers to the right of 3,169, will they be in the solution set?
No.
No. Anyway, you could have done that computation using a machine, plugging in an actual reasonable number input instead of an extreme input. So that tells us what the solution. It's not any numbers to the left of 631. It's not any numbers to the right of 3169. It's numbers between. So the inequality should apparently be solved by 631 to 3169. Should I include or exclude endpoints? Exclude. Because those endpoints produce a revenue that is exactly equal to a million. And did we want revenues exactly equal to a million or strictly greater than?
Strictly greater than.
Strictly greater than. So we should exclude endpoints. How do people feel about that? That seem okay? Yeah. Oh, yeah, absolutely. Yeah, sorry, I should have seen you come in and so that one actually had an application behind it. Ooh, I guess we should put units back in. So places between those two places will produce a revenue greater than 1 million. I'm going to, for the remaining examples, kind of forget about the applied nature of this. And I'm just going to say let's solve some inequalities. And we'll see a few different phenomena that can happen. And then on page 3, there will be a general guideline for what are all of the phenomena that could possibly happen. So page 3 will wax just a little bit abstract, but I don't think it'll be too bad. Let's keep on solving. So here's a polynomial, x squared plus 4x minus 12. Let's determine all of the x values which result in that polynomial being greater than or equal to 0. Reasonably explicit, but no motivation. That's okay. So what is this asking us to do? It's asking us to solve this inequality. And we have the same plan of attack. We'll start by solving equality. And the numbers in this problem look like they maybe were even cherry-picked so that the numbers will work out well. Maybe it doesn't look that way, but they happen. What would people rather see then? Quadratic formula, completing the square, or factoring? Any one of those will work.
Factor.
Great, let's factor the thing. So I guess in order to factor this polynomial, I need two numbers that multiply to 12, but one positive, one negative, and which add to 4. So I guess one positive, one negative means they need to subtract. So two numbers that multiply to 12 that subtract to 4.
6 and 2 is 0.
Perfect. Yeah. So that means I'll want x plus 6 times x minus 2. I want to set that equal to 0 and solve for x, but that's easy to do because it's factored. The only way two things can multiply together to be 0 is if one of them is 0. So what are the solutions to that equation? And I think instead of trying step 2 as above, I'll go for the alternate approach. So here's one thing I know so far. I know that this function, its graph will go through the point 2, 0, and its graph will go through the point -6, 0. Will the graph of this function, it's a quadratic function, so it'll be a parabola, upward opening or downward? Upward opening? So let's just encode that in the graph. It'll be an upward opening parabola that passes through those 2 points. So the graph will have to look something like that. And that's a cartoon graph. There's very little detail in it. But let's just see if that's enough detail to solve the question. If I take numbers to the left of -6, will they solve the inequality?
Yes.
You look at those x values, the corresponding y value is positive. I want positive y values. So it looks like everything from -infinity to -6 will solve the inequality. Does x equals -6 itself solve the inequality?
Yes.
Yeah, because x equals -6, well, we found -6 by setting it equal to 0, but we want to solve when f of x is greater than or equal to 0, so equal 0 is just fine. Numbers between, x values between -6 and +2, will those x values solve the inequality? Well, let's see. If I take that x value, what can you tell me about the corresponding y value?
It's negative.
It's negative. Negative numbers don't solve this. I want to know when f of x is bigger than or equal to 0. So numbers between -6 and 2 do not satisfy the inequality. What about numbers bigger than 2? They do? Nice. How do people feel about that? So since we know what the graph of a parabola should look like, we don't need to explicitly plug in sample points. We can look at the graph and just visually see what the solution to the inequality will be. This next one, I think maybe I just want to be quiet for a bit. So here's another inequality. X squared plus 4x minus 5 is strictly less than 0. I say that this one's for you, and I think I mean it. Do people want me to talk through this example? Do people want me to keep talking? Okay, then I'll be quiet, and I'll say you guys can think about this for a little bit, go through those steps. And if you come down to a solution, whichever techniques you used, feel free to compare with those around you. Comparing with those around you will not be allowed on Monday. Groovy. So let's jump right to the final answer. What is the solution to this inequality? Yeah.
-5 to 1. Don't include either one.
Cool. So, I guess one thing I could have done while you guys were doing that was walk it myself, but I didn't. That answer agree with everyone else? Anyone get anything different? Does anyone want me to talk through this example? Maybe I will just a little bit. I'll, like the one approach, solve the equation. What technique did you use to solve the equality?
Factoring.
Factoring. That's a good choice. You'll get the two solutions, and then you can graph the thing and just see what the answer should be. Cool. So the remaining two on this page are so picked because different phenomena will occur. So in the example, the three examples so far, when you solve the quadratic equation, you got two solutions. Does every quadratic equation have two distinct solutions? Always at most, but there could be just one or there could be none. So let's think about what that means for an inequality when you get one of those two situations. So let's do this one. Let's take this polynomial, x squared plus 4x plus 12. Let's find the x values which result in that polynomial being less than or equal to 0. So step one, solve the equality. What techniques would people like to see? I guess quadratic formula or completing the square?
Quadratic formulas.
Sure. Maybe I'll do both. Let's try the quadratic formula. So by the quadratic formula, I see that the solution to this should be x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So there's that so far. And let's just look inside of that parentheses. That's 16 minus 4 times 12. 16 minus 4 times 12, will that be positive or negative?
Negative.
Negative, right? 4 times 12 is bigger than 4 times 4. So I see a negative number inside of a square root. If I see a negative number, am I allowed to see negatives inside of square roots? So the quadratic formula says that this equation has no real solutions. As maybe another strategy, the 4 is an even number and the polynomial has leading coefficient 1, so it's easy to complete the square. I see that this polynomial should be the same thing as x plus 2, quantities squared, because that'll give me the x squared term. It'll give me 2x and 2x adding up to 4x. But if I FOIL this out, I'll wind up with just a 4 as the constant term, which is not big enough. I need to get 12, so plus 8. So there's the thing that I need to set equal to 0. And if I try to solve that directly, I'll get x plus 2 equal to plus or minus the square root of negative 8. And again, I get the same issue, negative inside of a square root. Okay, so there are no solutions to equality. What that means is the places where equality happens are where the inequality, well, where the places where the polynomial is equal to 0 are the places where it could conceivably change from being positive to negative or negative to positive. So it can never change from positive to negative or from negative to positive. So it's either always positive or always negative. How do you think we could decide which?
Plug in 1 and negative 1.
Yeah, not even that. Let's plug in 1. We just need to plug in one value. So let's plug in 1. So let's compute g of 1. We'll get 1 squared is 1 plus 4 times 1 plus 12. Is that total positive or negative?
Positive.
Yeah, maybe you know it's 17, but I don't care that it's 17. So it's positive somewhere, and it can never change from positive to negative. So it's positive everywhere. So what's the solution to this inequality? It's just everything, right? Oh no, it's the opposite of everything.
Nothing.
If this polynomial is positive everywhere, when is this polynomial non-positive?
Never.
No. So there are no solutions to g of x less than or equal to 0. What if the problem had been changed? What if I instead asked you to solve the inequality g of x strictly bigger than 0? Then what would the solution have been?
All real numbers.
All real numbers. Let's also just see this from a graph. I went and completed the square right here, so that makes this thing easy to graph. Let's see if we can read off the same solution from a graph. So I found so this will be an upward opening parabola with vortex at -2, 8. So if there's -2, 8 not drawn to scale, the graph will look something like that. Is that ever negative? No. So we see the same thing from the graph there. How does that seem? That seems reasonable? That makes sense? So the last thing that can happen is, so that's what happens when there are no solutions. Another thing that can happen is the polynomial equation might have a single solution. I know it says to do this on your own time, but I want to do this because there's an interesting thing that will happen. Let's solve this equation. If g of x is x squared minus 2x plus 1, let's solve g of x is strictly bigger than 0. And let's start with this. Solve the equality. What x value solves that?
X minus 1.
Cool. So this polynomial factors as x minus 1 squared. When is that equal to 0? Yeah, that's the only solution. So there is a single solution to this equation. That can happen sometimes. So there's only one x value, namely x equals 1, where this graph has any chance of changing from positive to negative or negative to positive. And let's think about this 2 different ways. It could conceivably change from positive to negative at x equals 1. Let's just check if it does. What's an x value to the left of 1?
0.
0. When x equals 0, what do we get for this polynomial?
1.
Which is positive. So the solution will include all numbers bigger than 1. All numbers less than 1. So all numbers less than 1 satisfy g of x bigger than 0. What's an x value that's bigger than 1?
2.
When x equals 2, it looks like we get for g of x, I think 1 again, right? Right, one could check that. 2 squared is 4 minus 2 times 2. So that's 4 minus 4 plus 1. Yeah, that's 1. Which again is bigger than 0. So all numbers greater than 1
satisfy g of x greater than 0. So I'm going to say something which will be not quite correct. So if all numbers greater than 1 solve the inequality and all numbers less than 1 solve the inequality, does that mean that all numbers solve the inequality? No, why not?
1 doesn't.
And 1 actually doesn't, right? You plug in x equals 1, you'll get 0, which is not bigger than 0. So the solution to this inequality appears to be everything except for 1. Which, if you happen to like interval notation, there it is. That seems pretty okay? So what do you think? Will all quadratic inequalities break down into basically one of these 3 cases? Yeah. So let's just write down everything. So suppose I give you any degree 2 polynomial, ax squared plus bx plus c. And I ask you to solve polynomial bigger than k, or bigger than or equal to, or less than or equal to k, for some number k. Well, let's just see what happens. So in the case that I want to do a little bit of color coding, did I not bring the colors and pens? I'll be okay. So there will be 3 cases. Either there will be 2 distinct solutions to f of x equal to k. Let's call them x1 and x2. And let's even say x1 comes before x2. So I know that this function will pass through y equals k at 2 points, those 2 points. In the case that a is bigger than 0, so a is the leading coefficient in the polynomial, will the graph open upward or downward? The upward opening? So the graph of the polynomial will look something like this. And now we can just read off solutions. F of x is bigger than or equal to k. Well, we want the space between those 2 solutions or beyond? Beyond. Negative infinity to the smaller of the 2 solutions to equality, together with the second solution on to infinity. How will it change if I want to get f of x strictly bigger than k?
Non-inclusive.
Yeah. Well, I want to have the exact same solutions, but I want to throw out the points where y is equal to k. That's just x1 and x2. If I want less than or equal to k, it looks like I want the space between. If I want a strict inequality instead of loose, then I'll exclude endpoints. That seem pretty okay? How do you think the answers will change if I instead deal with the case that a is negative?
It'll flip.
They'll somehow there will be some flip that happens. So in the case that a is less than 0, I'll have a polynomial that looks something like this. So now when I want bigger than or equal to k, it looks like I want between. When I want less than or equal to k, I'll want extreme values. That seem reasonable? And on the one hand, like, there's a table that encodes everything. But if I gave you a single example, do you think you could just draw a picture of the graph and know what the answer should be? Yeah. So even if you don't remember what these are, remember the procedure. Find the two solutions, draw the graph. You know if it opens up or down. Doesn't even have to be a good picture of the graph. Then you can read off when the y value is bigger than or less than whatever y value you pick. Let's keep on going. The next case is there is a single solution, x0. So what does that mean graphically? That means that there is only one x value, which results in a y value of k. The only way that can happen is if that's where the vortex is. So in the case that it's upward opening, the graph will look something like this. So let's read off the answers. So if the graph is upward, well, given that graph, tell me when is f of x bigger than or equal to k?
All the time.
All the time? Negative infinity to infinity? When is f of x strictly bigger than k?
Negative infinity to x of 0 together with x 0 infinity.
The only place where it isn't is at this point x0. What if I want to know when f of x is less than or equal to k? Well, is f of x ever less than k? Is f of x ever equal to k? At one point. So how many points are there where f of x is equal to k?
X is 0.
Just the one. And I'll put it in set braces just to emphasize that it's a set of numbers that happens to contain only one number. When is f of x strictly less than k?
Never.
No.
Perfect. Do you think we'll get similar answers if we have the parabola opening downwards instead?
Yes.
Yeah. So in the case that a is less than 0, the parabola will open downward. It'll look something like this. And you can read off the same solutions. I think I won't in the interest of getting to more examples. The other case that can happen is maybe f of x equal to k has no solutions. That is to say, this line at y equal to k is never crossed by the graph. Well, in that case, well, we can still draw the picture. In the case that a is bigger than 0, we'll have an upward opening parabola that never crosses that green line. So that must mean the vortex is somewhere to the north of that green line. So we'll have a graph that looks something like that. Looking at that graph, when is f of x bigger than or equal to k?
All the time.
When is f of x strictly bigger than k?
All the time.
So what answers go on the next two lines?
Never.
Nice. So let's go through this for one of these two. And then we'll do something on the next page. So let's solve this inequality. X squared plus 2x plus 4 strictly bigger than 0. So step 1, solve equality. What are the solutions to that when you replace it with equality? So step 1, solve x squared plus 2x plus 4 equals 0. And I'm just being quiet because it's my intention that you guys are like probably already solving that. Do people want me to solve that equation? Okay, then I'm just going to be quiet till someone tells me what the solution to the equation is. while that's happening, I'm going to hand back that group quiz from a while ago. I will do so by listing all of the names of the people in the group, and the first person who wants it will get it. Tate and Emma. Alvin, it's yours. Group 1, Trevor, Will, Taylor, Jacob. No one else expressed desire, so. Zach, Emma, Claudia, Josh. Alvin. Sydney, McConkey, Sabrina, Nick, and Albert. Okay. You guys don't seem to really want these back. I guess you did get feedback on the day of. Chris L, Victoria, Katie, and Megan. Okay, hearing no demand. Abby, Ben, Rowan, and Harry, Group 5. In fact, if that's the case, you guys can ask for them right after class if you want them. The demand doesn't seem to be there. Okay, cool. Let's do this. So what are the solutions to that equation?
Negative infinity to negative 4 non-inclusive, union 1 to infinity non-inclusive.
So that was the solution to the whole inequality. It was negative infinity to
Negative 4 non-inclusive, union 1 to infinity.
Cool. Does that agree with everyone? Do people want me to talk through it otherwise? Okay, yeah, let's do it. So, step 1, let's solve the equation. What were the solutions to that equation?
X plus 4, x minus 1.
Yeah, that's how it factors. So the actual solution are those two. Does that agree with everyone else? Well, they disagree with me, so I'm going to go through and resolve it. So I'll use completing the square. So this is the same thing as x plus 1 quantity squared plus 3 equals 0. I suspect that your factoring was incorrect. Right, you said x plus 4 and x minus 1?
Yeah.
I think that would put a 3 on the middle term instead of a 2. No, that would give it 2. X equal to negative b plus or minus the square root of b squared minus 4
Wait.
a.
Is that for x squared plus 3x squared and 4?
Oh, yep. Okay, you did. That was about a different problem than I was doing.
Okay.
Okay, cool.
That makes more sense.
Yeah, so no solutions, right?
Yeah.
Okay. So, I infer from this that when I asked the question, did anyone get a different answer, you all are a bunch of liars, right? Yeah, I want to gauge for, is there, even if that were a correct answer, which I didn't work out in advance, it seemed wrong to me, but even if it were all right, I would want to see if people had different answers, so less lying, please. Okay, so no solutions to equality. So apparently then the only options are either the inequality should be solved everywhere or never. Should this inequality be solved everywhere or never? Let's draw a picture. So there's the line at y equals 0. I want an upward opening parabola, and I know that it will never cross it, so it'll look something like that. So it looks like it is always positive. To solve the inequality, it looks like the inequality is solved by negative infinity to infinity. And this is super messy because why do I even bring pens to class? Why don't I just use pencils? Because I do everything wrong. So let's close with one last application. So the last application I want to hit is let's think about what you need to do when you want to compute the domain of a function that involves a square root. And this might not seem like it immediately involves solving an inequality. Let's do that top one. So this time I am actually going to go in order to avoid that same confusion. I want to solve that. I want to compute the domain of that thing. And the only thing that I can see that could possibly go wrong is the square root. What types of numbers can I see inside the square root?
Anything positive.
Anything positive. Maybe I'll be pedantic and say, well, you mean anything non-negative. Because the square root of 0 makes sense, so 0 is allowed. I can see anything that's bigger than or equal to 0. So if I want to compute the domain of this, I just need to know when the thing inside the square root, 1 minus x squared, is bigger than or equal to 0. Does that look like an easy inequality to solve? Yeah, let's go through the motions. When you solve equality, what do you get? I think plus or minus 1. Is it plus or minus 1? Okay. So those are the places where it could possibly change. Sketching a cartoon graph. I know it goes through negative 1, 0, and 1, 0 because of this observation. Upward opening or downward opening? Is this parabola upward opening or downward? Downward. So the graph will look something like that. And I want to know when is that bigger than or equal to 0. So do I want the space between those roots or the space beyond? Between? I want to know when the y value is bigger than or equal to 0. So I want those values. So it looks like the solution is the interval from negative 1 to 1, inclusive or exclusive. And one last thing in the 25 seconds I have, we can check if this is reasonable by allowing a computer to graph the thing. Let's plot the function given by the square root of 1 minus x squared. And let's just see if the domain, if the graph looks right. So looking at that graph, God damn it. Looking at that graph, is the domain the interval from negative 1 to 1? Yeah, I guess from the picture you can't tell whether those numbers should be included or excluded. But we know they shouldn't. You can literally plug them in. So, what will happen next time is I will finish our discussion of quadratic functions by introducing complex solutions to quadratic functions. And on Monday, there will be that quiz. And if you didn't get your group quiz back, and you want it back, I'm going to be standing here. Perfect. Which group were you?
Oh, that group.
You guys want to see it?
I was so excited. You were.
Yeah, I assume that was just like.
So check marks are good.
Check marks are good. Okay. Yes.
In particular, you lost only 1 point. What did you do? Okay, yeah, so -1, like that one is actually on the quiz one.
Sounds good.
Yeah.
It was so bad. I hate Van. I hate Van.
Yeah.
Yeah, and in particular, it's like the quizzes, the total weight on the quizzes is only 10%. And there are going to be a great many of them.
Yeah, it won't kill our grades failing. Well, we didn't.
No,
You didn't even
you did fine.
It's just like, ah, now I see it. I could have done it.
Yeah, I mean, that's the point of these quizzes, right? They're supposed to be reasonably low weight, but enough stakes that you like try so that you're on.
Thank you very much. Appreciate it.
Yeah, have a good day.
Thank you for responding to my email so fast the other day. I've never had a professor email me that fast after I send the email.
Oh, you must have
Well,
emailed me
formatting.
before one of my periodic email checks.
Well,
What
it's
did you
it's
ask?
just like, I asked about like what the homework, what I did wrong on the previous one. 'Cause I had
Okay.
27 out of 39. I read your email, I changed it for this past week's. So
Okay.
hopefully it's better, but
Perfect.
again, thank you for emailing so fast. I never had a professor email that fast. It was like,
Oh, well,
sweet.
it's all luck, right? Like occasionally you make it to the bus stop right before the bus.
I've never done the bus over here at, of like to Upper Campus or whatever. I've never tried it.
Oh, and any bus, right? Sometimes
Oh,
you make it to the bus stop right before the bus.
Fair, fair.
Sometimes you make it to my email right before an email check.
Well, that's awesome. Thank you very much.
Have a good day.
Thank you, you too.